Hello one and all. Welcome to this session of surface areas and volumes. Today we will discuss something really interesting, and for that I want you guys to listen to me carefully. Suppose a company is planning to start a new business of selling ice creams and they decide to distribute it in cones as well as in cups. But before they start doing so, they need help regarding two things. First, how much quantity of ice cream this cone and cup can hold, and second, how much paper they will require to wrap each of these two shapes. And that's where our role comes into picture. As a mathematician, we have to help them out with these two important criteria. Okay, so let us take them one by one. Friends, here we are talking about the quantity of ice cream that these two shapes can contain, right? Which means we actually intend to find the volume of these two shapes itself. So to find the volume, let us think about another shape which is relatively similar to a cone. And what comes to my mind is a right circular cylinder. See, that actually makes sense because both of these shapes have a circular top. Then comes a curved surface, with the only difference being that cylinder shows another circular surface at the other end, whereas the curved surface of cone seems to taper and as such has no other circular surface. So we can try to learn volume of a cone with the help of a cylinder. So suppose in both these shapes we try to keep two parameters same. First, the diameter, and second, the height. Next thing we try to do is to fit the cone into that cylinder. And now if you look at it, the cone will seem to be just 1/3 of a cylinder. This is often used as a way to remember the volume of the cone. We all learned in our previous session that the volume of a right circular cylinder is pi r square h. So it was found by many great mathematicians that volume of cone is 1/3 pi r square h, that is 1/3 of the volume of a cylinder. So now say if the company decided to use a cone with the radius of 2 centimeters and keeps the height of the cone to be 10 centimeters, then the quantity of ice cream that can be filled to the brim of the cone is actually the volume of the cone itself. So all we have to do is substitute these values of radius and height into this formula 1/3 pi r square h, and what we'll get is 41.9 centimeter cube, or if we round it up, then it is 42 centimeter cube of ice cream, or 42 centimeter cube is the volume of the cone. Now let's discuss about volume of the cup. If you go to see an ice cream cup, it is a lot like a cone, with a slight difference being that it's not completely tapered like a cone. Or we can say if we cut a cone, then we'll get a smaller cone and a shape like an ice cream cup. In the language of geometry, we call this shape a frustum. And since we carve it out from a cone, so this in particular can be called frustum of a cone. Before we proceed to find the volume of the cup, let us first understand this shape of the cup in contrast to the cylinder and the cone. So let us consider a cone, a cylinder and a frustum and keep their parameters same, just like we did before. We will keep their radius and their height similar. Now in such a condition, if we try to fit a frustum into the cylinder, it will look as if the upper circular surface of both of these shapes will be same, but there will be a difference when it comes to the lower circular base, because the lower circular base of the frustum is little smaller than that of the cylinder when they have the same parameters. In the same way, let's say we try to fit even a cone inside a frustum. Now even its upper circular surface will be same as the cylinder and the frustum, but since a cone doesn't have any base, so it will look like a point. So when all of these three shapes will be seen together by keeping their parameters same, the arrangement will look something like this. And I hope this kind of arrangement has helped you to understand these shapes better. Okay, now let's get back to the volume of the frustum. Friends, just remember one thing, the volume of a frustum is also very similar to the volume of a cone. we have studied just now, it is 1 by 3 pi r square h. But as we have seen, in a frustum there are two circular surfaces with different radii. So even in the formula, 1 by 3 pi h will remain the same, and we have to just play around with this r since there are two circular surfaces. So if we consider the radius of first circular surface to be r1 and radius of the second circular surface to be r2, then we can replace this r square by an expression r1 square plus r2 square plus r1 r2. So if we are able to somehow remember this minor difference, then it becomes all very easy. Now suppose the company wishes to sell the same quantity of ice cream in the cup also as they sold it in a cone, which means they want the volumes of cone and cup to be same. Then what exactly should be the height of the cup in order to contain 42 centimeter cube of ice cream, which we just calculated for the cone? Now that we know the volume of cup or frustum, so let us equate it with the volume of cone and try to find the height of the cup. And by doing so, the height will come out to be 5.71 centimeters. In order to match the volume of the cone, the parameters of the cup should be height 5.71 centimeters, upper and lower radii 2 centimeter and 1 centimeter respectively. Now guys, did you notice something over here? Even when the height of the cup is less than that of the cone, even then they contain same quantity of ice cream. And we often tend to think that cone contains more ice cream. So that's the kind of strategy that is often used by certain companies to increase their ice cream sales, you see. Anyways, moving forward, let us calculate how much paper the company will require to wrap each of these two shapes. And we'll try to calculate for both simultaneously. Okay. The paper or lid with which we cover the top of the cone as well as the cup is always a circular shape, right? So for that surface, we can use formula for area of the circle, which we already know is pi r square. But in cup, there are two circular surfaces. So for that, we can use pi r1 square and pi r2 square for two different radii. And company has already given us information about the radius of the circular surfaces. So we will just substitute those information in these formulas and we'll get the area of the circular surfaces for both the shapes, which is 12.56 centimeters square for the lid of the cone. And if we talk about the cup, then it is 15.7 centimeters square of paper for both lid of the cup and the bottom circular surface. Now the only thing left to find is the paper required to cover the side part of these shapes, which is called lateral surfaces. And since the side surface is smooth and curved in case of a cone, frustum and cylinder, so it's also called a curved surface. In a cone, the curved surface starts with the circular opening and gets tapered to form a pointed end, correct? So it's almost as if a circle is decreasing layer by layer until it becomes a point. Since a circle is involved, so we'll write pi r, and we have to cover the entire lateral surface with the wrapper. So the height or distance along this lateral surface from the pointed end to the circle is called slant height, denoted as L. Now please note, slant height is different from the middle perpendicular height, which we denote as h, remember? We use that height to find the volume. But to find the surface area, we don't require the middle perpendicular height, but instead we require the height along the curved surface, which is the slant height. But there is a slight glitch. Company has provided us the information about the radius and the perpendicular height, and as such we know nothing about the measurement of the slant height. Well, believe me, this too can be calculated very easily. If you carefully notice, the radius, perpendicular height and the slant height form a right angle triangle, where the slant height acts as the hypotenuse or the largest side. And we all know we can use Pythagoras theorem in context of a right angle triangle in order to find the hypotenuse. So by using the same, we can find the slant height first, which will come out to be 10.2 centimeter in this case, and then eventually we can use the slant height for calculating the curved or lateral surface area, which will come out to be 64.04 centimeters square. That means for covering an entire cone, we need 64.04 plus 12.56 centimeters square of paper, which will come out to be 76.60 centimeters squares. So combining the area of upper circle and the lateral surface, we can get the total surface area of a cone. Now talking about the cup or the frustum, the curved surface doesn't get tapered completely, but it ends with a circular base. Since there is an additional circle involved here along with the curved surface, so we'll write pi r1l plus pi r2l. Now even here we don't know slant height for the cup, so mathematics helps us with even that by using Pythagoras theorem. And the slant height for the cup we'll get is 5.8 centimeters. Now if you substitute it in the formula for curved surface, we'll get 54.60 centimeters square. So the total requirement of paper for the cup will be 54.6 plus 15.7, which will be 70.3 centimeters squares. So guys, here we can see the difference between the requirement of wrapper for each of these two shapes. From the calculations we can see cup requires approximately 6 centimeters squares of lesser wrapper than that required by the cone. So if a company were to decide economically between these two shapes, they'll definitely go with the cup or the shape of a frustum, as they will have to spend lesser amount on the wrapper. But friends, let us leave these kind of decisions on these companies. It's up to them to decide what's best for their business. What we should feel happy about is the fact that as a mathematician, we not only help them out, but we also along the way learned some important tools to find surface area and volume for a cone and a frustum. Till then, keep watching, keep learning.